Good afternoon to all. Welcome to this 49th lecture session of the course Computational Fluid Dynamics. So in the last lecture, we have started our discussion on grid transformations. Today also, we will try to go through the topic of grid transformations only, and we will try to see some of the specific examples that how we can apply different transformations from one plane to another plane. Okay. So in terms of, if I talk about the different methods which are available for transformation of grids, so we generally follow three different strategies. So the very first one is algebraic transformations. Okay, so in case of algebraic transformations, we are having some algebraic expression for algebraic expression for one coordinate system to another coordinate system. So it means our transformation functions, for example, say zeta will be some algebraic expression. I can write a1x plus a2 x square plus a3y, something like this. So I'll be having some algebraic expressions which will be actually relating the transformation from one coordinate system to another coordinate system. Okay. Second type of transformation function we may have as complex transformations. So in case of complex transformations, we will be having our functions in the form of complex parameters. For example, I can have x plus iota y equal to say some function of zeta plus iota eta. Okay, so I'll be having in terms of the complex parameters, I will be having actually transformation functions involved. And third type of transformation is actually PDE based transformation. So where we are having some partial differential equation, okay, and that differential equation is actually representing transformation from one coordinate system to another. For example, say xy coordinate system to zeta eta coordinate system. If I have to move from one to another, I have to do some of the transformations. I require some transformation functions. Basically, these transformation functions will be in the form of partial differential equations. Okay, so this is the broad idea about what kind of transformation functions we may have. Now let us try to see the specific examples. Okay, so if you recall, yesterday I have given you one task that if we are having some grid where in xy coordinate system, which is nothing but our physical plane, where in physical plane we are having actually non-uniform mesh structure. Okay, and this is our zeta eta plane, which is nothing but a computational plane. And in this computational plane, what we are having, in this computational plane, we are having our uniform structured mesh. Okay, so this type of requirement in our physical plane is where we are having actually wall bounded flows. In case of wall bounded flows, we will be finding that velocity profile is something like this. So near the wall, we will be having actually large gradient of the velocity. So in order to capture the large gradients of the velocity, we have to go for very fine mesh. So that is what is being done over here. But when we have to employ the finite difference formulation, we want uniform structured mesh. So that's why we have used some transformation in order to convert this non-uniform structured mesh from physical plane to computational plane. And in the computational plane, we are getting this mesh in some structured fashion. Okay. So one of the thing why this mesh is called stretched mesh, because in computational plane we are having the spacing between the elements as nothing but uniform. For example, delta eta in y direction. However, when we are shifting it to delta y plane, there those spacing between 2 points in xy plane, in terms of eta it is same. So in terms of eta it is delta eta only everywhere. But when we are transforming it to y, that same delta eta distance is actually being stretched. For example, near the wall, this delta eta is appearing very small, and over here the same amount of delta eta is actually appearing as a very large distance. Okay, so that's why this type of grid is called as actually stretched grid, where a same uniform space in one coordinate system is actually appearing as with some different sizes in the another plane. Okay, now with this type of grid, for example, what I will be having here, we were having some spacing delta x and delta y. However, delta y was not uniform and delta x was uniform. So when we will be transforming, obviously xy we need not to do any transformation, because xy it is already uniform. So if xy it is already uniform, I can simply write zeta as nothing but equal to x. And in case I have to see this transformation for y, that same amount of distance delta eta has to be represented differently. So here, as I think one of the students replied yesterday, that we have to consider some logarithmic formulation in order to use this transformation along the y direction. So obviously, when we will be considering eta, we have to consider some function of log over here. Okay. So now, even if we consider the log, so one is we are having some linear equation, and in another case we are having some logarithmic equation. So this type of transformation, what we have to apply over here, this is nothing but example of the algebraic transformation. Here, when we are shifting from physical plane to computational plane, our transformation functions are nothing but taking the form of transformation functions are taking the form of algebraic expressions. Okay, so now let us try to see the details. So what I have done, as I told you that in x direction we are not having any non-uniformity, so that's why I can simply say that zeta is equal to x. However, in y direction, because same distance, we are actually representing with different y values in the physical plane. So that's why we have to use this transformation eta equal to ln y plus 1. Okay, so if we use these expressions for direct transformations, our inverse transformation function will be x equal to zeta and y equal to exponential of eta minus 1. So if I take exponential of both sides, it will be becoming eta equal to y plus 1, and y I will be getting as eta minus 1. So this is nothing but inverse transformation function. So this is a simple algebraic expression. So that's why we are easily able to obtain direct as well as the inverse transformation functions. Okay. Then now what we have to do, because finally we have to now convert our governing equations from xy plane to zeta eta plane. Okay, so once we will be converting governing equations, we have to find out these parameters. So these are nothing but the matrices over here. So dy by d eta will be becoming equal to eta, and this dy will be becoming eta into del eta. And if I write in average or finite change, in terms of finite change, I can say that delta y is nothing but e times eta into delta eta. So it means same distance delta eta is multiplied with exponential of e eta, and corresponding to that we are getting our value of delta y. Okay, so in terms of giving you idea, it is the case, say this is my eta equal to 0, then I have eta equal to say 0.1, eta equal to 0.2. So if you see what is happening when we are moving from wall, away from the wall, the value of eta is increasing. Okay, so this will actually result in increase of e eta, and the e eta multiplier with constant distance delta eta, because between these different constant eta lines we are having same spacing. So when this pre-multiplier will be multiplied, we will be getting amplification in value of y over here. Okay, so that's why delta y is becoming over here e eta times del eta. Now what we have to do, we know that in our physical domain, continuity equation is del rho u by del x plus del rho v by del y equal to 0. So if I have to transform this continuity equation in zeta eta plane, I will be getting this particular final equation. So this is something which is actually based on the formulations whatever I described yesterday. So yesterday we have seen the formulation of del by del x and we have seen the formulation, sorry, we have seen, yes, we have seen the replacement of del by del x in terms of del by del zeta and del by del eta. Similarly, we have seen the conversion for del by del y also. Okay, so considering these conversions, we will be getting this particular equation as nothing but our continuity equation in the zeta eta plane. Okay, so now this continuity equation, if you see, we are having some matrices over here: del zeta by del x, del eta by del x, del zeta by del y, and del eta by del y. So we know the direct transformation functions. Once we know direct transformation functions, I can find out values of these coefficients, and my continuity equation finally will be taking the form in terms of zeta and eta. And similarly, if I multiply with eta on both sides, I will be getting this particular as my final continuity. Okay. So the way we have converted this continuity equation, in the similar way we have to also convert momentum equations when we are talking about the adiabatic flow situation. And if heat transfer is also involved, then we have to also convert first the temperature equation into zeta eta plane. And as in zeta eta plane we are having uniform structured mesh, there we can easily employ our finite difference method, and we can find out the solution of parameters on this zeta eta grid. Okay, once we have found the solution on zeta eta grid, because for each corresponding to each grid point, we are having some mapped parameter corresponding mapped point in xy physical plane. So we can transform that solution from zeta eta plane to nothing but our xy plane. Okay, so how to apply this overall procedure for like stretched or compressed grids by using the algebraic transformation functions? Is this clear?
Yes, sir. Yes.
Okay. Now let us talk about the next arrangement, which is of body fitted coordinate system. Okay, so what I have say some diverging section. Okay, and say flow is happening through this diverging section. So considering the symmetry of the problem, I can consider this center point as my axis of symmetry, and in place of solving for the entire domain, I will only solve this for one half of the domain. Okay, so this one half of the domain of this diverging section is actually shown over here. So this is my y, this is say x direction. So in this xy direction, I have plotted this particular solid boundary. This is the solid boundary, and this is inside our flow domain. Okay, now in this flow domain, in order to perfectly capture the boundary of the body, we have actually considered boundary fitted coordinate system. Okay, so it means that whatever this grid points we are considering, these grid points we are considering parallel to the boundary in order to mimic the boundary properly. Okay, so in my mesh structure, now you can see this F and G is becoming nothing but axis of symmetry. So this is the symmetry boundary, and this particular line over here is nothing but a wall boundary. Okay, now what we will be considering, obviously we have to transform this from xy system to zeta eta system. So in this direction, let us consider these lines are nothing but different constant zeta lines. So for this line, zeta is constant. Here also we are having some zeta as constant. Similarly, we will be considering these boundary fitted lines as nothing but constant eta lines. Say this is my one eta, this is another eta, so like that. Okay, now in x direction, once again, if you see, we are having uniform spacing, so that's why we need not to use any method, any further transformation. So that's why I will simply writing zeta equal to x. Now if I consider y, so what kind of function I can choose for y to just establish that point? I am writing eta equal to y divided by ys, where ys is nothing but some function of x. Okay, so ys I am considering some function of x. Now I have considered that I have some points D, C, and E as my boundary points on this, sorry, as my grid points on the boundary of the domain. Okay. So now if I want to calculate value of eta at point D, so value of eta at point D will be becoming nothing but yd divided by ys corresponding to point D. So that will be becoming simply as yd will be nothing but value of y at this point. So which is, and y as I am writing as function of x, so I can simply write it will be ys xd and ys xd. So it means corresponding to this point, I have value of eta as nothing but 1. And similarly, if I try to find out the value of eta for point C, for point C also it will be becoming yc by ys, and yc I can write ys corresponding to xc, and ys is function of xc when I am calculating at point C, so I can simply write it as xc, so that will be becoming equal to 1. So at the moment, if you compare, yc is greater in comparison to yd, because this distance of point C is higher in comparison to distance of point D. But for both the points D and E, we are having same value of eta. So I can consider that along this entire boundary, we are having some fixed value of eta, which is equal to eta equal to 1. So it means once I will be transforming this particular grid from xy Cartesian system to zeta eta system, I will be finding that this bottom line will represent some value of eta, and corresponding to that value of eta, we are having the occurrence of this bottom flat boundary. So F and G points, this is corresponding to the center line. And this top boundary over here, now here it is having different values of y, but this entire line is having same value of eta, which is equal to eta equal to 1. So that's why whatever this top boundary we will be getting in zeta eta system, so corresponding to eta equal to 1, all the points will be actually collinear. So these points D, C, E, etc. will be collinear. So it means this top line is nothing but represents the upper boundary of our simulation domain, which was curved in physical plane. In computational plane, it has become nothing but a flat boundary. And similarly, I'll be having other lines also with different values of eta. Okay. So this is an example of boundary fitted coordinate system. So the last example was corresponding to Cartesian coordinate system, where we are having stretched or compressed meshes in the physical plane. In this example, we are having boundary fitted coordinate system, but this boundary fitted coordinate system, with the help of only algebraic manipulations, can be transformed from xy non-uniform unstructured mesh to zeta eta uniform structured mesh system. Okay. Now let us consider some another complicated example where the algebraic expressions will not be sufficient enough to transform our grid structure from one plane to another plane. Okay. So this is another example of a boundary fitted coordinate system. So in this boundary fitted coordinate system, we are having some aerofoil. So you can see this inner boundary is nothing but the boundary of the aerofoil structure. Okay. Now on this aerofoil structure, we have actually created some boundary fitted mesh. So you can see one is this edge is actually becoming part of our mesh. Then we are having another edge which is surrounding this, then another edge, another edge. So like this, we are having this type of mesh structure over here, which is actually exactly fitting the boundary. Okay, so this particular type of mesh which exactly fits the boundary is called as O type grid. Okay, so this type of grid is called as O type grid. If in this O type grid, let me draw one aerofoil. If in this O type grid, near the trailing edge, instead of forming a closed circle, if I form lines something like this. Okay, so now I am not forming closed structure for all the lines, rather I am joining these lines with the trailing edge. I am joining these lines with the outlet boundary of our physical domain. So under this condition, this type of mesh, so this is my solid boundary and these are my mesh structure. So this type of mesh structure is called as actually C type mesh. Okay. And one more popular arrangement is used for aerofoil system. If I consider my aerofoil is something like this, say I'm hatching this just to represent the solid boundary. And if I consider this is my inflow plane, this is outflow plane, and instead of just using O-type arrangement, the way we have arranged grids in case of C-type mesh at the outlet edge. Similarly, if we arrange in inlet edge also, and we also try to fit the boundary of the body, something like this, by using this type of mesh structure, then we get some specific mesh structure which is called as nothing but H-type mesh. Okay, so this information just I am giving to you, that if you want to create mesh over the aerofoil, so what are the popular strategies which people are using? So one is to enclose completely. When we are enclosing completely with the help of some extended circles, then we are calling this as O-type grid. When one side is open, we are calling it as C-type mesh, and when both sides are actually open, then we are calling it as H-type mesh. Okay, so this is a general detail about the creation of mesh over airfoil structure. Now let us focus on this particular O-type grid. Okay, so in this O-type grid, if you see, we have created some boundary fitted mesh, and we are in XY coordinate Cartesian coordinate system. So you can see over here our lines of the meshes are actually, grid lines are not parallel to X and Y. Okay, and if these lines are not parallel to XY, so what we have to do, obviously, if we have to apply finite difference method, we have to transform this into some zeta-eta coordinate system. Okay, so for doing that, what we have to do, first I have located different points over here. So you can see this point E, C, D, F, then some point P, R, Q, S, A, B, etc. Okay, now you can see this point E, G, P, R, A, C. These all are lying on inner boundary of the aerofoil, or I can say inner boundary of this grid. Okay, so for aerofoil it is actually the outer edge, but for this grid structure it is the inner boundary of the grid. So what I am doing, I am representing this inner boundary of grid with some function gamma 1. So what I am saying, say my gamma 1 is some function which is representing the inner boundary of mesh. Okay, and in order to construct this gamma 1, we are having set of known XY points. So we are having set of known XY points. For example, at this E, I have some value of XY. At this point, I have some another value of XY. At this point, another value of XY. And the locus of all these points, whenever it is joined with a curve, that is actually defining our curve gamma 1. Okay. Similarly, for defining the outer boundary of the mesh. So like this, we will be obviously creating this mesh depending upon our requirement. And once we are having the occurrence of far field, means we are far away from the far away from the location where effect of wall can be felt, then we will be actually stopping our grid creation, and at that point we can apply far field boundary. Okay, so corresponding to this outer boundary of the mesh, we are having, say, some function gamma 2, which represents actually the outer periphery of this mesh. Okay. Now, as we are having these lines, will be representing different constant zeta conditions, and these particular circular lines will be representing different constant eta conditions. Okay. For example, for inner boundary, I have considered eta is constant, that is something like eta 1, and for this outer boundary, I have some another eta value as eta 2. Okay. So now, if I transform this grid into computational domain, it will be looking something like this. This is my zeta, this is my eta, and I have now uniform structured arrangement, and all these points, whatever we have represented, you can see over here, the points E, C, A, R, P, G, which were lying on inner boundary. So these points were actually lying over here. So because of this, I can say that this is nothing but my gamma 1, which is the inner boundary. Okay, and you can find the points which were there on outer boundary F, D, B, S, Q, H, etc. So these points are actually forming the part of this top boundary. So that's why I'm calling this as nothing but my gamma 2 function. Okay. So till this point it is clear. Whatever I
Yes, sir.
Okay. Now question comes that in this diagram I have represented something that we are in this system XY system, and over here we are in zeta eta system where we are having actually uniformly structured arrangement. Okay. But question comes that what kind of transformations we have to apply from one system to another system in order to obtain this transformation. Okay. So that is a very, very important question. Now to answer this question, let us physically try to understand this. So as I told you that this inner boundary of the grid is something which is represented by gamma 1, and at this boundary all the parameters are actually, all the xy values are known to us. How xy values are known to us? Because in this physical plane we are knowing this boundary of the aerofoil. So corresponding to that, we can locate different xy values. So it means I can say that this is something my boundary, and at this boundary I am knowing all the values of xy. So that's why I can simply say that boundary conditions are known at gamma 1. Okay, so at gamma 1 all the boundary conditions are known. Similarly, I can say that this is my outer boundary, and obviously once in the physical domain we will be creating some mess. We will be always aware of all these coordinates which are actually lying on the boundary of this mess. Okay, so I will be knowing the details of all these coordinates from our geometric considerations while we have created the mess. Okay, so I can say that at this outer boundary gamma 2 also, at gamma 2 also all BCs are known to us. Okay, so it means if we try to see mathematically, it is becoming some situation which is similar to that of elliptic partial differential equations. Okay, so this is one very, very important point. What I am trying to say, that for this surface gamma 1 which is representing the inner boundary, we are knowing all the values of coordinates. Similarly, for outer boundary gamma 2 also we are knowing all the coordinates. Okay, so it means for inner boundary and outer boundary of this domain, we are knowing the boundary conditions. If we are knowing the boundary conditions, it means mathematically this problem can be related to the situation of elliptic equations, where also we are having the known boundary conditions, but in between we have to do computations, and we consider that whatever the values we are having at the boundaries, these actually propagate into the domain. Okay, so this mathematical similarity with this physical arrangement is clear to you? Is this point clear? Abhishek and Saurav?
Sir, not exactly. Like how to interpret that
So what I am
nature will be.
Yeah, so how I am saying nature will be elliptical is because in case of elliptic physical situation, what we are having, say this is my domain. Okay, we consider that if boundary conditions for any field is known at all the boundaries, and if I want to predict value at any point within the domain, say my temperature condition, I know here 50 degrees Celsius, here 100 degrees Celsius, here say 150, here say 250. Okay, so now if I want to predict the value of temperature at this center point, so value of temperature at this point will be something which will be influenced by the values known at boundary. Okay, so similar is the situation over here. For this outer boundary, I am knowing different values of xy. Sorry, for this inner boundary. Similarly, for this outer boundary also, I am knowing the values of xy. Now, what will be value of xy in the center points? That is something I can estimate if mathematically I am able to represent this with the similar situation of elliptic like path differential equation. Is this one clear now?
And sir, all the boundary conditions should be Dirichlet.
Yes.
Okay.
Dirichlet
And
or any other. Dirichlet or any other. See, this is something which I am trying to explain the physical nature. Over here, we are not concerned about yet governing equations. Okay, so we are not yet concerned about governing equations. We are now mainly discussing how to transform the geometric parameters. So basically, we are considering that geometric parameters are known as boundaries. Now, with the help of these boundary geometric parameters, we have to compute geometric parameters for the within the, okay.
and sir, what I was thinking is that can't we use a polynomial fitting, because we know the normal at the boundaries and the coordinate at the boundaries. So we
See,
know four informations.
for this particular arrangement, with this much coarse detail of the mesh, you may even do. But when you will be having even very more complicated structures, then it will not be possible. Okay, so what we are trying to do with the help of this example, we are trying to actually generalize the procedure. Okay.
Okay, sir.
So what we will be doing now, as I told you that this particular situation is becoming something like elliptic equations. So that's why I can write that del square zeta by del x square plus del square zeta by del y square will be equal to 0. So this is a Laplace equation, and the nature of this equation is nothing but elliptic. Similarly, for eta also, I have written del square eta by del x square plus del square eta by del y square equal to 0. So it means now zeta and eta are our dependent variables and x and y are independent variables. So what we are trying to do, actually, we are saying that if we know the value of if we know the values known at boundaries, by using these equations, we will be able to predict the values of zeta and eta within this domain. Okay, so what I can do, because I know the values at boundaries, so after solving these equations at different points, I will be able to find out the values of zeta and eta. Okay, so this is the forward transformation, but we are mainly interested in inverse transformation, because in this computational plane, we will be considering some structured uniform mesh, but we are interested that corresponding to each point, once we found the solution, what is the corresponding point in the XY plane. Okay, so to do that, what we are doing now, if we just do some mathematical manipulations by considering zeta and eta as independent variables. So what I have done, I have considered these two equations only, but in these two equations, we will be now doing some mathematical manipulations by considering zeta and eta as independent variables and xy as dependent variables. Okay, so this is one important point. We are doing some manipulations in order to go for inverse transformation. So we are considering that in zeta eta coordinate system, we are having some independent variables and xy as dependent variables. Okay, so once we do this inverse mathematical formulation and we try to convert these two equations into the new system of equations, we will be finding something like this: alpha times del square x by del zeta square minus 2 beta into del square x by del zeta del eta plus gamma times del square x by del eta square equal to 0. And similarly, I will be finding this another equation for y, and what are the values of alpha, beta, and gamma that we are having. Okay, so it means over here now we are now talking about inverse transformations. It means that we have considered some uniform grid in the computational plane, but that uniform grid, now corresponding to this, we have to locate the points in our physical plane. Okay, so for that purpose we are trying to do this. Okay, so if I have to now solve these new equations, so these are now my new set of elliptic equations. So if I have to solve these elliptic equations, So for having inverse transformations, I have to once again supply the boundary conditions. Okay. So if you see over here, this is something uh, as our bottom boundary, or which is corresponding to inner surface of the mesh. At this point, we are knowing the boundary conditions. At this point also, we are knowing the boundary conditions. This is the outer boundary. From physical plane, we are knowing, but we are finding some new boundaries, gamma 3 and gamma 4 over here, at which our boundary conditions are not known to us. Okay, and if we have to solve these equations during the inverse transformations while we are mapping our solution from zeta eta system to xy system, we have to solve these equations. So that's why we have to supply all the boundary conditions. Okay, so in order to do so, what we have to do, we have to know the boundary conditions for this gamma 3 and gamma 4 surfaces. Okay, so for that purpose, what we are doing, just to explain you, I am saying that I have created some cut section over here. It means I have sliced something. So once I slice something, I have taken a very small cut of this surface in physical plane, say by using some knife or hacksaw. Okay. So once I have made this small cut, I will be finding my wedge-like structure over here. And in this wedge-like structure, say this top portion is something which represents gamma 3, and P and Q points are corresponding to that. So that's why you can see this P and Q points corresponding to gamma 3, and R and S points correspond to gamma 4. Okay, so I have some points R and S corresponds to gamma 4. So this just difference in between gamma 3 and gamma 4, I have represented with different lines only just to highlight or give you the idea that how we are creating this boundary. But in actual practice, what we will be doing, we will not be making any physical cut over here. Rather, we will be having only a single line, and on the top face of that single line, we will be considering that our points are nothing but Q and P, and in the bottom face, so bottom face of this particular line, we will be considering that our points are nothing but R and S. So we are saying that we are having some common line whose top part is acting as boundary for gamma 3 in actually our computational plane, and bottom part is acting as gamma 4. And once again, in the physical domain, once we have created this mesh, so we will be having known values of xy parameters for this point P, all the points which are basically lying along this particular line. So that's why from this previous, whatever I have shown in the previous slide, from there I can say that at all these node points also, from physical plane, our boundary conditions are known to us. Once we are knowing all the boundary conditions, then what we have to do, whatever these equations I have represented over here, these equations we have to solve using these boundary conditions. And once we solve these equations actually will be helping us in representing corresponding points. For example, this is point A over here now, so it will be giving me the coordinate of point A over here during the inverse transformation in physical plane. Okay, so this type of procedure, which is used for transformation of meshes on like from one system, xy system, to zeta eta system, it is called as elliptic grid generation. And this type of grid generation is actually based on some partial differential equations. Okay, so now let me make one point very clearly, that till this point we have not solved any equations for flow field. Okay, we have not solved continuity momentum equations. Till this point, whatever equations we are solving, these equations are nothing but enabling us to transform from one coordinate system to another coordinate system. Okay, so these partial differential equations over here are only including the geometric details. These are not considering the flow conditions and how flow will be evolving. For that, we have to actually solve continuity and momentum equations. Okay. Now let me give you one idea. Of computational plane with boundary conditions. So this is now our computational plane in zeta eta system, and this computational plane now is only first for geometric transformations. Okay, and at the all the boundaries we are knowing values gamma 1, gamma 3, gamma 2, and gamma 4. And if I have, say, any point A on this grid structure, and if I want to calculate the corresponding value of xy, I have to solve this equation using finite difference method, and from that finite difference approximation I will be able to calculate the value of xy, and these xy, once I plot in my physical plane, that will be representing the point corresponding to our O grid structure. Okay, because in the O grid structure, because in this zeta eta plane, whatever the boundary conditions we are taking, these boundary conditions are corresponding to the shape of this O grid structure. Okay, so that shape of O grid structure is something which is known at the boundaries, and by using these elliptic equations, that is being transformed into the core of the domain. Okay, this point is clear.
So, sir, boundary conditions for the coordinates are on us how to select those values.
Sorry,
We can manipulate, sir, like we can manipulate the values of eta and c
yes.
at the boundaries.
For boundaries, we can take any random value, and based on that arbitrary value, there will be propagation. Okay.
Yes, sir.
Now, let me also explain you one important point. Once we have done this grid transformation, geometric transformations, after that we have to also do transformations for our continuity and flow equations. Okay. So for flow equations and continuity equations, we will be finding that we will be having occurrence of some matrix. Okay. So for finding these matrix, what we require sometimes del zeta by del x, del zeta by del y, del eta by del x, and del eta by del y, something like this. So how to find out these? Obviously, because now we are having some differential equations, and these differential equations are nothing but partial differential equations, so for which closed form of the solution is not applicable. So under these scenarios, while we will be transforming the equations from one plane to another plane, there also we have to apply nothing but finite difference approximations only. Okay. So for example, if I have to find out del zeta by del x at any point I comma j, using the central difference approximation, I can write it as zeta at I plus 1 comma j minus zeta at I minus 1 j divided by x I plus 1 j minus x I minus 1 j. So once we have solved basically the geometric equations, after that I will be knowing the values of zeta corresponding to each xy or xy corresponding to each zeta and eta. Okay. So after we have known these zeta eta, then with the help of this numerical approximations, we can calculate matrix, and these matrix then can be substituted into our governing equations in order to transform from one coordinate system to another coordinate system. Okay, so this point is clear.
Yes, sir.
Okay, so now with this I conclude this particular course on computational fluid dynamics. Obviously, there are some more things which one can discuss in detail about the multi-phase computational modeling, multi-fluid computational modeling. There are some particle-based methods also, but as this is beyond the scope of this particular course, if say you get some opportunity to have some course on advanced computational fluid dynamics in future, then you can go through these lectures. At the moment, whatever the content we have covered in these 49 lectures, with that I am formally concluding this course on computational fluid dynamics. And obviously, if you are having any questions for that, you can write to me and we can have separate doubt clearing sessions. Okay. All the best for your exam.